What if I told you that every photon of light touching your skin right now might be secretly connected to another photon on the opposite side of the universe, and that this connection travels faster than light itself, violating everything Einstein believed was possible? And what if the very mechanism creating this impossible connection is hiding in plain sight in the most abundant thing in our universe, light itself? In 1935, Albert Einstein called quantum entanglement spooky action at a distance and argued it proved quantum mechanics was fundamentally incomplete. He spent the last 20 years of his life trying to disprove it. He failed because quantum entanglement is real. It's been experimentally verified thousands of times. And here's what will absolutely shatter your understanding of reality. Light isn't just affected by quantum entanglement. Light might be the original source, the primordial mechanism, the cosmic thread that weaves entanglement into the very fabric of existence. By the end of this journey, you're going to understand why the light from your phone screen connects you to the Big Bang, why photons might be the universe's information network, and why some of the world's leading physicists now believe that light doesn't just carry entanglement. It creates it, sustains it, and might be the reason quantum mechanics works at all. But before we dive into this mind-bending revelation, do me a favor. Hit that like button right now and subscribe if you want more content that challenges everything you thought you knew about reality. And drop a comment telling me what country you're watching from and what time it is where you are. I'm genuinely curious to see how far across the globe this quantum knowledge is spreading. Are you watching from Tokyo at midnight? London at breakfast? São Paulo in the afternoon? Let me know. Now, let's start with what seems like a simple question. What is light? You've been seeing it your entire life, but I guarantee you don't actually understand what it is. And that's not your fault, because light is genuinely one of the strangest things in existence. Here's your first surprising twist. Light isn't actually moving through space the way you think it is. When a photon travels from the sun to your eye, from its perspective, no time passes at all. Zero, zilch, due to time dilation at light speed. If you could ride on a photon, you'd experience your entire journey instantaneously. The photon is created and absorbed in the same moment from its own reference frame. Think of it like this. Imagine you're watching a movie, but someone's holding down the fast-forward button at infinite speed. The entire movie plays in a single frame. That's what reality is like for a photon. This isn't science fiction. This comes directly from Einstein's special relativity, published in 1905. The equations are crystal clear. As you approach light speed, time slows down, and at exactly light speed, time stops completely. This means every photon exists in a timeless state, connecting the moment of its creation to the moment of its destruction with zero elapsed time in between. Now here's where it gets weird. If no time passes for a photon, then from the photon's perspective, where is the distinction between here and there? If you experience no time, you also experience no distance. The entire path collapses into a single point. A photon emitted from a star 13 billion light years away experiences that entire journey as happening at a single location. Let me give you an analogy to wrap your head around this. Think of reality like a giant piece of paper. For us, moving through space is like an ant crawling across the surface of that paper, which takes time. But a photon is like a needle punching through the paper. It connects 2 points, the point where it enters and the point where it exits. But from the needle's perspective, those aren't 2 separate points at all. They're the same point, just accessed from different sides of the paper. This is important because it's setting up something profound about entanglement. Keep this idea in your mind. Light exists in a state where space and time collapse into unity. But what actually is light made of? Is it a wave or a particle? The answer is both, and this is where quantum mechanics enters the picture. In 1905, the same year Einstein published Special Relativity, He also explained the photoelectric effect, which proved that light behaves as discrete particles called photons. But we've known since Thomas Young's double-slit experiment in 1801 that light also behaves as a wave, creating interference patterns. This is called wave-particle duality, and it's not just a quirky property of light. It's fundamental to quantum mechanics. Here's what's mind-blowing. A single photon can interfere with itself. Send one photon at a time through a double slit, and over time, it builds up an interference pattern, as if the photon went through both slits simultaneously and interfered with itself. The photon exists in a superposition, a state where it's taking all possible paths at once until you observe it. And this brings us to the quantum measurement problem, which is one of the deepest mysteries in physics. When you observe a quantum system, it collapses from existing in multiple states simultaneously to existing in just one state. Before you measure which slit the photon went through, it goes through both. After you measure it, it went through only one. The act of observation changes reality. Niels Bohr, one of the founders of quantum mechanics, argued in the 1920s that this was fundamental. Quantum systems don't have definite properties until they're measured. Einstein hated this idea. He believed reality existed independently of observation, famously asking, "Do you really think the moon isn't there when you're not looking at it?" This disagreement between Einstein and Bohr sets the stage for entanglement. Because Einstein was about to discover something that he thought would prove quantum mechanics was wrong, but instead, it proved quantum mechanics was far stranger than anyone imagined. Hold on, because what I'm about to tell you is going to completely flip your understanding of cause and effect. And it all started with a thought experiment that Einstein designed to destroy quantum mechanics. Instead, he accidentally discovered the most profound connection in the universe. But to understand why this matters for light, we need to first understand what entanglement actually is and why it seems impossible. Picture this. You have a pair of gloves in a box. You split them up, putting one glove in a box sent to Tokyo and one in a box sent to New York. When someone in Tokyo opens their box and finds a left-hand glove, they instantly know the person in New York has a right-hand glove. That's just correlation, right? The gloves were always that way. Opening the box just revealed pre-existing information. Now forget everything about that analogy, because quantum entanglement is nothing like that. Here's what actually happens. Imagine those gloves don't exist as left or right until someone opens the box. Both boxes contain gloves that are simultaneously left and right, existing in a superposition of both states. Then, the moment someone in Tokyo opens their box and observes a left glove, the glove in New York instantly, and I mean instantly, faster than light could travel between them, becomes a right glove. Not because it was always a right glove, but because the measurement in Tokyo forced it to become one. That's quantum entanglement. And yes, it's been experimentally verified thousands of times. In 1935, Einstein, working with physicists Boris Podolsky and Nathan Rosen, published a paper that became known as the EPR paradox. They argued this scenario proved quantum mechanics was incomplete. Einstein believed in local realism, the idea that objects have definite properties regardless of observation, realism, and that no information can travel faster than light, locality. Entanglement seemed to violate locality because measuring one particle instantly affected its partner, regardless of distance. Einstein proposed there must be hidden variables, information carried by each particle, that predetermined its behavior, like our gloves example. This would preserve both realism and locality. Quantum mechanics would just be an incomplete description missing these hidden variables. For 30 years, this remained a philosophical debate. Then in 1964, Irish physicist John Stuart Bell published a theorem that changed everything. Bell's theorem provided a mathematical test to determine whether hidden variables could explain quantum mechanics. He derived an inequality, Bell's inequality, that any local hidden variable theory must satisfy. If quantum mechanics was right and Einstein was wrong, experiments would violate Bell's inequality. Here's the mind-blown moment. When physicists actually did these experiments, starting with John Clauser in 1972 and culminating in Alan Aspect's definitive experiments in 1982, Bell's inequality was violated. Einstein was wrong. There are no local hidden variables. Quantum entanglement is real, and it really does involve what appears to be faster-than-light influence. But here's the crucial detail that often gets missed. Entanglement doesn't allow faster-than-light communication. You can't use it to send messages. Here's why. When you measure an entangled particle, you get a random result. Sure, the other particle instantly has a correlated result, but the person measuring that particle also sees randomness. It's only when you bring the two sets of measurements together and compare them, which requires sending information through normal, slower-than-light channels, that you see the correlation. Think of it like this. Imagine you and a friend are each flipping coins, but the coins are entangled. Every time you flip heads, your friend flips tails, and vice versa. But from your individual perspectives, each coin flip looks completely random. It's only when you get together and compare notes that you see the perfect anti-correlation. That's why entanglement doesn't violate causality, even though it seems to involve instantaneous influence. But this raises a profound question. How do the particles know what result to give? If there are no hidden variables, no predetermined information, then how does measuring one particle instantly determine the state of another particle light years away? And here's where we start to introduce the revolutionary idea. What if light itself is the answer? What if photons, in their unique timeless and spaceless existence, are the mechanism by which entanglement propagates through the universe? Because here's something that's going to blow your mind. The most common way to create entangled particles in laboratories is through light. Specifically, through a process called spontaneous parametric down conversion, where a single high-energy photon splits into two lower-energy photons that are perfectly entangled. Light creates entanglement. But what if it's more than that? What if light doesn't just create entanglement in lab experiments, but is the fundamental carrier, the cosmic infrastructure of entanglement itself? Let's get specific about how scientists actually create entangled particles, because this is where light's central role becomes undeniable. The most common method uses a non-linear optical crystal, typically made of beta barium borate. You shine a stream of photons into this crystal. Most photons pass straight through unchanged, but occasionally, about 1 in every billion photons, something extraordinary happens. The photon splits into 2 photons. These are called signal and idler photons. Here's the crucial part. Conservation laws apply. The original photon had a certain energy and momentum. The 2 daughter photons must have energies and momenta that add up to exactly match the parent. But quantum mechanics says each individual photon exists in a superposition of multiple possible energy states until measured. So both photons are created in a superposition, but they're correlated entangled such that whatever energy one has, the other must compensate. The same thing happens with other properties. Photons have a property called polarization, which is the direction the electromagnetic field oscillates. You can think of it like the orientation of a wave. Light can be vertically polarized, oscillating up and down, horizontally polarized, oscillating side to side, or any angle in between. It can even be circularly polarized, rotating as it travels. When you create 2 photons through down conversion, they're entangled in their polarization. Here's a common setup. The crystal is oriented so that if you measured them, you'd find that whenever one photon is vertically polarized, the other is vertically polarized, and whenever one is horizontal, the other is horizontal. And this is the quantum part before measurement. Each photon is in a superposition of both vertical and horizontal polarization. They exist as both simultaneously, yet they're perfectly correlated. This isn't theoretical. You can buy entangled photon sources commercially now. Companies like Thorlabs sell turnkey systems. Universities around the world have hundreds of these setups. Entangled photons are the workhorses of quantum information science. But here's what's fascinating. Why photons? Why is light the preferred medium for creating and distributing entanglement? Part of it is practical. Photons don't interact with each other or their environment much, so they can maintain entanglement over long distances. In 2017, Chinese scientists used a MISHIS satellite to distribute entangled photons between ground stations 1,200 kilometers apart, setting a distance record. But I'd argue it's deeper than just convenience. Photons have unique properties that make them fundamentally suited for entanglement. Remember how I mentioned that photons experience no time and no distance? This means that from the photon's perspective, the two entangled photons, even if they're separated by kilometers or light years from our perspective, are at the same place in time. Think about that. We see two separate particles in different locations, correlated in impossible ways. But from the photon's perspective, there's no separation at all. They're not two things connected across space. They're one thing that we perceive as two, because we experience space and time. Here's an analogy. Imagine you're looking at your reflection in a mirror. You see two faces, yours and your reflection's. You raise your left hand, and simultaneously, the reflection raises its right hand. It seems like instantaneous correlation across space, right? But of course, there aren't really two separate things. There's just one thing, you and your reflection. It's just another perspective on that same thing. What if entangled photons are similar? What if they're not two separate particles that are mysteriously connected, but rather two different perspectives, two different slices of a single photon that exists in the timeless, spaceless perspective where photons actually exist? This isn't just poetic speculation. There's a mathematical formalism in quantum mechanics that supports this view. It's called the Wheeler-Feynman absorber theory, developed by John Wheeler and Richard Feynman in the 1940s. They proposed that a photon doesn't travel from point A to point B like a little bullet. Instead, the photon is a transaction between the emitter at point A and the absorber at point B. The photon is the connection itself, not a thing traveling along the connection. In this view, a photon exists as a four-dimensional structure in spacetime, with one end at the emission event and one end at the absorption event. From our three-dimensional perspective, moving through time, it looks like a particle traveling, but that's just our limited perception. Now extend this idea to entangled photons. If each photon is a spacetime structure connecting emission to absorption, then two entangled photons, created from the same parent photon, are both connected to that parent event. They're not separate particles that happen to be correlated. They're branches of the same underlying structure. And here's where it gets truly wild. If photons are fundamentally structured this way, and if entanglement is created through photon interactions, then light isn't just one way to create entanglement. Light might be the underlying mechanism that creates and sustains all entanglement in the universe. Every entangled particle pair, even electrons or atoms, might trace back to photon interactions. Light might be the skeleton key, the universal connector, the cosmic web that makes quantum entanglement possible. But to understand why physicists are starting to take this seriously, we need to dive deeper into what photons really are and what they're made of. What is a photon made of? It's a particle, so it must be made of something smaller, right? Wrong. A photon is an elementary particle. It's not made of anything smaller. It's an excitation of the electromagnetic field, a ripple in the fabric of spacetime itself. Let me explain what that actually means, because it's crucial for understanding light's role in entanglement. In quantum field theory, the most successful theory in the history of physics, every particle is understood as an excitation of an underlying field. The electromagnetic field permeates all of space. When that field gets excited, when it vibrates in a particular way, we observe a photon. Think of it like the surface of a pond. The water is always there, spread across the entire pond. When you throw a stone in, it creates ripples waves traveling across the surface. Each ripple is a localized excitation of the water field. Photons are like that, except instead of water, it's the electromagnetic field, and instead of a pond, it's all of spacetime. Einstein extended this in 1905, proposing that light actually exists as these discrete particles, not just that it's emitted and absorbed that way. This was controversial. Even Planck initially resisted it, but Einstein turned out to be right. So a photon is a quantum of the electromagnetic field. But here's what's deeply strange. The electromagnetic field is relativistic. It's built into the structure of spacetime, according to special relativity. The electric and magnetic fields are actually two aspects of the same thing, appearing different depending on your motion. An electric field in one reference frame looks partly magnetic in another frame. And remember, photons travel at the speed of light, which means they exist in that weird relativistic regime where time stops and space contracts. A photon is inherently a relativistic quantum object. It fully embodies both quantum mechanics and special relativity. This makes photons unique. Electrons, for example, are quantum objects, but they travel slower than light, so they experience time and space the way we do. Photons are the only particles we regularly interact with that exist in this timeless, spaceless regime. And here's where it connects to entanglement. Quantum entanglement is also a fundamentally relativistic phenomenon. When you have two entangled particles separated in space, different observers moving at different speeds won't even agree on which measurement happened first. In one reference frame, you measured particle A first, so it collapsed first, and then instantaneously affected particle B. In another reference frame moving relative to the first, particle B was measured first. Both perspectives are equally valid. There's no absolute fact about which measurement happened first. This seems paradoxical until you realize that entanglement isn't about one particle sending a signal to another particle. It's about a correlated quantum state that exists in spacetime as a unified whole. The spacetime structure of entanglement is non-local spread out across space. And photons existing in a regime where space and time collapse are perfectly suited to carry this non-local structure. A photon is non-local by its very nature. It connects two spacetime events, its creation and destruction, without experiencing the space or time between them. Let me give you another analogy. Imagine you're looking at a long stick. If you wiggle one end, the other end moves. From your perspective, it seems like a signal traveled along the stick. But now imagine you're a two-dimensional being living on the surface of a table, and the stick is actually a three-dimensional object passing through your 2D plane. You see two circles, the two ends of the stick, that move in a correlated way. You have no idea there's a three-dimensional stick connecting them because you can't perceive that third dimension. Entangled photons might be similar. We exist in three spatial dimensions plus time, and we see two separate photons with correlated behavior. But photons exist in a different regime, where time is collapsed and space is contracted. From that perspective, the two separate photons might be aspects of a single unified structure that we can't fully perceive, because we're confined to our space-time perspective. Now, I know what you're thinking. This is getting pretty abstract and theoretical. Fair enough. But here's the thing. This isn't just philosophical speculation. There are specific, testable predictions that come from taking seriously the idea that light is the source of entanglement. And some of the most cutting-edge experiments in quantum physics right now are exploring exactly these predictions. Let me tell you about some of these experiments, because they're going to blow your mind. In 2015, a team led by physicist Nicholas Gizin at the University of Geneva conducted an experiment that most people have never heard of. but it's one of the most important tests of quantum mechanics ever done. They created pairs of entangled photons and sent them through fiber optic cables to villages 18 kilometers apart. Then they measured each photon's polarization at the exact same moment, or as close to the exact same moment as possible, within nanoseconds. Here's why this matters. If there's any communication between the photons, any signal traveling at light speed or slower, it wouldn't have time to travel 18 kilometers in a few nanoseconds. So if the measurements are still perfectly correlated, it proves the correlation can't be due to any signal traveling between them. The result? Perfect correlation, violating Bell's inequality by more than 11 standard deviations. That's a 1 followed by 27 zeros to 1, against this being a coincidence. The photons were correlated in a way that no local hidden variable theory can explain. But here's the detail that's relevant to our discussion. The experimenters used incredibly precise timing. They used random number generators to decide, independently at each location, which angle to measure the polarization at. These decisions were made so close to the measurement time that even if a signal traveled at light speed from one detector to the other, it wouldn't arrive in time to influence the measurement. This is called closing the locality loophole. Earlier experiments had left open the possibility that some signal could travel between detectors. This experiment proved that's impossible. The correlation is truly instantaneous, in violation of what we'd expect from classical physics. But notice, this entire experiment is about photons. The entanglement is between photons. It's distributed by photons, traveling through fiber optic cables, and it's measured by detecting photons. Light is central to every aspect. Now let me tell you about an even more mind-bending experiment. In 2012, a team led by physicist Jiaosong Ma at the Institute for Quantum Optics and Quantum Information in Vienna conducted something called an entanglement swapping experiment. Here's how it works. You create two separate pairs of entangled photons. Call them A, B, and CD. Photons A and B are entangled with each other, and photons C and D are entangled with each other, but there's no connection between the pairs. Now you take photons B and C1 from each pair, and you measure them together in a special way called a Bell state measurement. This measurement doesn't tell you the individual states of B and C. It tells you something about their relationship. Here's the wild part. The moment you do this measurement on B and C, photons A and D, which have never interacted, which were created by completely separate processes, which have no causal history connecting them, become entangled with each other. You've created entanglement between particles that never met. Think about how bizarre this is. Particle A was entangled with B. Particle D was entangled with C. You measured B and C together, and suddenly A and D are entangled, even though A and D are far apart and have never interacted. The entanglement was swapped. But here's what's relevant to our topic. All four particles in this experiment were photons. The entanglement swapping occurred through photon interactions. And this raises a profound question. If you can swap entanglement between photons like this, creating connections between particles that never met, what does that tell us about the nature of entanglement itself? One interpretation is that entanglement isn't a property of individual particles. It's a property of the photon field itself. When you create entangled photons A and B, you're not giving properties to A and B individually. You're creating a structure in the electromagnetic field that manifests as correlations between A and B. When you measure B with C, you're restructuring that field, and the structure now manifests as correlations between A and D. In this view, light, the electromagnetic field, is the medium in which entanglement exists. Entanglement is a pattern in the field, and photons are how we observe and manipulate that pattern. Now let me tell you about the most ambitious experiment in this domain, the Mises satellite I mentioned earlier. In 2017, Chinese physicists led by Jianwei Pan successfully distributed entangled photons from a satellite in low, Earth orbit to two ground stations 1,200 kilometers apart. This was a massive achievement, overcoming enormous technical challenges. Why is this important? Because as photons travel through Earth's atmosphere or through fiber optic cables, they interact with matter. They can scatter off air molecules or defects in the fiber. Each interaction risks destroying the entanglement, a process called decoherence. It's incredibly difficult to maintain entanglement over long distances through matter. But in the vacuum of space, photons can travel essentially undisturbed. The Mises experiment proved that entanglement can be maintained over huge distances if you use the vacuum of space as your transmission medium. And again, notice, photons are the particles being entangled and distributed. Light is the carrier of quantum information. Now here's where we start to connect all these pieces into a unified picture. We've seen that light has unique properties: timelessness, spacelessness, non-locality. We've seen that light is the primary tool for creating and distributing entanglement in experiments. And we've seen that entanglement can be swapped and restructured through photon interactions, suggesting that entanglement is a property of the electromagnetic field itself. But there's an even deeper level to this story, because some physicists are now proposing that light doesn't just create entanglement in laboratories. Light might have created all the entanglement in the universe, stretching back to the Big Bang itself. And this is where your mind is really going to explode. Let's rewind to the very beginning. The universe began 13.8 billion years ago in an incredibly hot, dense state called the Big Bang. In the first moments, the universe was so hot and dense that matter as we know it couldn't exist. It was a seething plasma of fundamental particles and radiation. Radiation means photons. The early universe was filled with light, so energetic that photons were constantly creating and annihilating particle-antiparticle pairs. The universe was opaque, meaning photons couldn't travel freely. They were constantly scattering off charged particles. Then, about 380,000 years after the Big Bang, something crucial happened. The universe cooled enough that electrons and protons could combine to form neutral hydrogen atoms. This event is called recombination, and it meant that suddenly, photons could travel freely. The universe became transparent to light. These photons have been traveling ever since, and we can still detect them today. They're called the cosmic microwave background, CMB radiation, and they fill the entire universe. No matter which direction you look in the sky, you see this faint glow of ancient light, cooled by the expansion of the universe from visible light to microwaves. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate noise from a radio antenna and kept detecting this persistent signal from all directions. They'd discovered the afterglow of the Big Bang, one of the most important discoveries in the history of cosmology. It earned them the Nobel Prize in 1978. Now here's the mind-blowing part. The CMB is remarkably uniform. The temperature is about 2.725 Kelvin in all directions, with tiny variations, only about 1 part in 100,000 across the sky. This uniformity is actually a huge puzzle called the horizon problem. Here's why it's a puzzle. Different regions of the universe that we see in opposite directions in the CMB have never been in causal contact. They're so far apart that even light, traveling since the Big Bang, hasn't had time to travel between them. So how did they end up at the same temperature? Normally, things equilibrate to the same temperature by exchanging energy, but these regions never had a chance to exchange energy. The standard solution to this puzzle is cosmic inflation, a theory proposed by Alan Guth in 1980. Inflation says that in the first fraction of a second after the Big Bang, the universe expanded exponentially fast, much faster than light speed. Before inflation, all regions of what would become our observable universe were close together and could equilibrate. Then inflation stretched them apart, so fast that they ended up beyond each other's horizons. But here's the quantum twist that's relevant to our discussion. During inflation, quantum fluctuations in the inflating field got stretched to cosmic sizes. These quantum fluctuations became the seeds of all structure in the universe. Galaxies, stars, planets, everything. And quantum fluctuations inherently involve entanglement. Think about it. In the quantum vacuum, particle-antiparticle pairs are constantly being created and annihilated. These pairs are entangled. During inflation, some of these pairs got stretched apart so fast that they couldn't annihilate. One particle ended up in one region of the universe, and its entangled partner ended up in another region, now beyond the horizon. This means the universe started out in a highly entangled state. Different regions that can't communicate with each other are nevertheless quantum mechanically correlated due to this primordial entanglement. And here's the crucial point. This primordial entanglement was created through the electromagnetic field. In the hot, dense early universe, photons were constantly interacting with matter, creating entangled states. Even today, every interaction mediated by photons, which includes most interactions in the universe, since electromagnetism is one of the four fundamental forces, creates or swaps entanglement. Some physicists, like Leonard Susskind at Stanford, have proposed that this quantum entanglement is fundamental to the structure of spacetime itself. In a series of papers starting in 2013, Susskind and Juan Naldecina proposed a principle called A equals EPR, which connects entanglement, EPR, referring to the Einstein-Podolsky-Rosen paradox, to wormholes, referring to Einstein-Rosen bridges, another name for wormholes. The idea is that entangled particles are connected by tiny wormholes in spacetime. The wormholes are so small that nothing can travel through them, so you can't use them for communication, but they provide a geometric picture of how entanglement works. Entangled particles aren't separate things mysteriously correlated. They're connected by a structure in spacetime itself. And if this is true, then the electromagnetic field, through which most entanglement is created and mediated, is literally stitching spacetime together. Light isn't just traveling through spacetime. Light is creating the connections that make spacetime a unified whole. Now, I want you to sit with that for a moment. Every photon of light, every electromagnetic interaction, is potentially creating or swapping quantum entanglement, which might be forming the very fabric of spacetime. Light isn't just the fastest thing in the universe. It might be the cosmic glue holding reality together. But we're not done yet, because this leads to an even more radical idea. What if consciousness and observation tie into this somehow? Not in a mystical way, but in a very specific, testable way related to how information is processed in quantum systems. And light, once again, is at the center of this story. One of the deepest mysteries in quantum mechanics is the measurement problem I mentioned earlier. Why does observing a quantum system cause it to collapse from a superposition of states into a definite state? What counts as an observation? Does it require a conscious observer, or is any physical interaction enough? The Copenhagen interpretation, championed by Niels Bohr, essentially said, don't ask. The wave function collapses upon measurement, and that's just how it is. Any attempt to visualize or explain what's really happening is meaningless. The math works, the predictions match experiments, and that's enough. But most physicists find this unsatisfying. Many alternative interpretations have been proposed. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses. Instead, every measurement causes the universe to split into multiple branches, one for each possible outcome. We only perceive one outcome because our consciousness is associated with one particular branch. Another interpretation, called decoherence theory, developed mainly in the 1970s and 1980s, provides a more physical picture. The idea is that quantum systems never truly collapse. Instead, when a quantum system interacts with its environment, which includes measurement devices, Air molecules, photons, everything information about the system spreads into the environment through entanglement. The system and environment become entangled in such a way that the system appears to have collapsed into a definite state, even though the overall system, quantum system plus environment, is still in a superposition. Think of it like this. Imagine you have a quantum coin that's both heads and tails simultaneously. When you look at it, photons from a light source bounce off the coin and enter your eye. Those photons become entangled with the coin's state. Some photons carry information about the head state, others about the tail's state. These photons then interact with the rods and cones in your retina, which interact with neurons in your brain, and so on. The information spreads and becomes distributed across trillions of particles. Now the coin still exists in a superposition of heads and tails if you consider the entire system, including your brain and all the photons and everything else. But from your perspective, as a subsystem embedded within this larger system, the coin has definitively collapsed to one state. And notice, in this picture, light plays a crucial role. Most information about the world enters your consciousness through photons. You see things because photons bounce off them and into your eyes. Even when you touch something, the reason you feel it is ultimately due to electromagnetic forces between the electrons in your fingertips and the electrons in the object, which are mediated by virtual photons. Light is the primary carrier of information from the outside world to your brain. And if decoherence is correct, then information spreading through entanglement is what causes apparent wave function collapse. This means light is directly involved in the process that creates our classical, definite-seeming reality from the underlying quantum superposition. Here's an experiment that demonstrates this. The quantum eraser experiment, first performed by researchers at the University of Maryland in 1982 and refined many times since. It's a variation of the double-slit experiment, but with a twist. You send single photons toward a double slit. Behind the double slit, you place detectors that can tell you which slit each photon went through. When you do this, the interference pattern disappears. No surprise they're observing. Which slit the photon went through collapses the superposition, and you get two bands instead of an interference pattern. But here's the twist. The detectors at the slits don't directly tell you which slit the photon went through. Instead, they create entangled photons. When a photon goes through the top slit, it interacts with a crystal that creates an entangled partner photon with one polarization. When it goes through the bottom slit, it creates a partner with a different polarization. The partner photons carry which path information. By measuring the partner, you could determine which slit the original photon went through. The result, even though you're not directly looking at which slit the photon went through, and even though the entangled partners are traveling off in a different direction, the interference pattern still disappears. The mere existence of which path information in the universe is enough to destroy the interference pattern. Now here's the quantum eraser part. If you do something to the entangled partner photons that erases the which path information, for example, passing them through a polarizer that makes both polarizations identical, the interference pattern reappears. Even though the original photon already went through the slit, already hit the screen, the interference pattern appears or disappears depending on what you do to the entangled partner photon. This experiment demonstrates that observation isn't about consciousness or eyeballs. It's about information becoming encoded in physical systems through entanglement. And the mechanism for this information encoding? Photon interactions. So light isn't just carrying information to your eyes so you can see the world. Light is creating quantum entanglement that determines whether reality manifests as a wave or a particle, as a superposition or a definite state. Light is the mediator between the quantum and classical worlds. And this brings us to something deeply personal, because we need to talk about how this affects you. Not humanity in general, not some abstract notion of consciousness, but you specifically, the person watching this video right now. Take a moment and look at your hand. Right now, photons from your screen or from a nearby lamp are bouncing off your hand and entering your eyes. These photons are mediating an entanglement between your hand and your visual cortex. Information about the position, texture, and color of your hand is being encoded into the quantum states of trillions of photons, which are then entangling with the molecules in your retina, creating a cascade of entanglement that ultimately produces your conscious visual experience. But here's what's profound. Those photons don't just carry information about your hand. They carry information about every interaction they've had throughout their entire history. A photon that bounces off your hand might have previously been part of the cosmic microwave background created in the early universe. Or it might have been emitted by a star millions of years ago, traveled through space, and eventually ended up in the light bulb illuminating your room. Every photon has a history written into its quantum state through all the entanglements it's participated in. And when that photon interacts with your eye, it's connecting you to that entire history. Think about that. You're not an isolated island of consciousness perceiving an external world. You're a node in a vast network of quantum entanglement that stretches back to the Big Bang. Every observation you make, every photon that enters your eye is extending this network, creating new connections, new correlations in a universal wave function. Let me give you a specific example to make this concrete. Look at the stars tonight, or remember the last time you saw them if you're watching this during the day. When you look at a star, photons that were emitted from that star years or centuries ago, depending on how far away the star is, are entering your eye. From your perspective, you're seeing the star as it was in the past. But from the photon's perspective, remember, no time has passed. The photon was created at the star and absorbed by your retina in the same instant from its reference frame. In a very real sense, looking at a star creates a timeless connection between you and that star. You and the star are entangled across spacetime through the photon that connects you. Now multiply that by the billions of photons entering your eyes every second. You're constantly being entangled with everything you see. Your quantum state is correlated with the quantum state of the entire visible universe. And it's not just vision. Your body is at 37 degrees Celsius, which means it's constantly emitting infrared photons thermal radiation. About 100 watts of power, roughly equivalent to a bright light bulb. These photons carry information about your body's temperature, your metabolism, your physical state. They radiate outward in all directions, interacting with the environment, creating entanglement between you and everything around you. You're not separate from the universe. You're intimately, quantum mechanically connected to it through an endless web of light. Here's an even more mind-bending thought. Some interpretations of quantum mechanics, particularly the relational interpretation proposed by Carlo Rovelli in 1996, suggest that properties of quantum systems only exist relative to other systems. There's no absolute state of a photon. There's only the state of the photon relative to you, or relative to some other observer. In this view, reality isn't a collection of objects with definite properties existing independently. Reality is a network of relationships, of correlations, of entanglements. You don't perceive an external world. You're entangled with the world, and that entanglement structure is what creates your experience. And light is the primary mechanism creating and mediating these relationships. When you see something, you're not receiving information about a pre-existing independent object. You're becoming entangled with that object through photon exchange, and that entanglement is what constitutes seeing. This might sound like solipsism or idealism, the idea that reality is just in your mind, but it's not. Other observers exist and create their own entanglement networks. The incredible thing is that these networks are consistent with each other. When you and I both look at the same object, we become entangled with it in correlated ways, and that's why we agree on what we see. The shared physical world emerges from the consistency of these entanglement networks. Now, before you start thinking this is all too abstract and philosophical, let me ground this in something very practical. Because understanding light as the source of entanglement isn't just intellectually interesting. It's leading to revolutionary technologies that are going to transform civilization in the next few decades. And these technologies are going to change your life in very concrete ways. Let's talk about quantum computing. You've probably heard the hype. Quantum computers will be exponentially more powerful than classical computers, solving problems that would take conventional computers billions of years. The reason quantum computers are powerful is superposition and entanglement. A classical computer bit is either 0 or 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 simultaneously. With n qubits, you can store 2n possible states simultaneously in superposition. 10 qubits can represent 1024 states at once. 50 qubits can represent over a quadrillion states. 300 qubits can represent more states than there are atoms in the observable universe. But superposition alone isn't enough. You need entanglement between the qubits so they can influence each other, allowing complex computations. And here's the challenge. Maintaining quantum coherence and entanglement is incredibly difficult. Any interaction with the environment causes decoherence, destroying the quantum state. This is where photonic quantum computing comes in. Several companies and research groups are building quantum computers using photons as qubits. Photons have several advantages. They don't easily interact with their environment, so they maintain coherence longer. They can be transmitted long distances through optical fibers for quantum communication. And we have excellent technology for manipulating light lasers, beam splitters, phase shifters, detectors. A Canadian company called Xanadu has built a photonic quantum computer called Borealis with 216 qubits. In 2022, they demonstrated quantum advantage solving a specific problem faster than any classical computer could using a photonic approach. But the most exciting application isn't quantum computing itself. It's quantum communication and quantum cryptography. Here's why this matters to you personally. Every digital communication you send, emails, messages, bank transactions, could potentially be intercepted and decrypted by a sufficiently powerful computer, especially once quantum computers become more capable. Quantum key distribution, QKD, solves this problem using entangled photons. The idea is beautifully simple. You share entangled photons between two locations. Because of the quantum measurement principle, any attempt to intercept or measure the photons disturbs them in a detectable way. You can use the correlations between the entangled photons to generate a random encryption key that both parties share, and you can be absolutely certain no one has intercepted it. China has already deployed quantum communication satellites and is building a quantum communication network connecting major cities. The MISHAS satellite I mentioned earlier isn't just a scientific experiment. It's the prototype for a quantum internet. Within your lifetime, probably within the next decade or two, quantum communication networks secured by entangled photons will become standard. Your financial transactions, your medical records, your private communications, all will be secured by the fundamental laws of quantum mechanics through entangled light. No future advance in computing power will be able to break this encryption because it's not based on computational difficulty. It's based on the laws of physics. But there's something even more profound coming. Quantum sensing. Entangled photons can be used to make measurements with precision beyond what's possible classically. This is called quantum-enhanced metrology. For example, gravitational wave detectors like LIGO use laser interferometry to detect incredibly tiny distortions in spacetime caused by colliding black holes or neutron stars. Current detectors are limited by quantum noise. The uncertainty principle limits how precisely you can measure the light. But using entangled photons, you can beat this limit. In 2019, the LIGO collaboration began testing quantum-enhanced sensing using entangled photons, achieving improvements over the classical limit. Future gravitational wave detectors will use entangled light to detect fainter signals from farther away, potentially observing the Big Bang itself through primordial gravitational waves. Medical imaging could be revolutionized too. Quantum-enhanced sensors using entangled photons could detect diseases like cancer at much earlier stages, potentially saving millions of lives. Some researchers are developing quantum microscopes that use entangled photons to image biological samples with minimal damage important, because the high-energy photons needed for high resolution can damage delicate biological molecules. Autonomous vehicles could use quantum LiDAR with entangled photons for navigation in fog or challenging conditions. Climate scientists could use quantum sensors to detect greenhouse gases with unprecedented sensitivity. The applications are endless, and they all rely on entangled light. But here's what I think is the deepest implication. Beyond any specific technology, we're learning to harness the fundamental structure of reality itself. For thousands of years, humans have manipulated matter carving stone, forging metal, synthesizing chemicals. For over a century, we've manipulated energy-generating electricity, harnessing nuclear power. Now we're beginning to manipulate quantum information, the deepest level of physical reality. And the primary tool we're using is light. Entangled photons are the interface between the quantum and classical worlds, the medium through which quantum information can be processed, transmitted, and utilized. In a sense, we're learning to speak the universe's native language. And that language is written in light. Here's something to think about. Consciousness itself might be a quantum phenomenon. This is controversial, and I want to be clear that most neuroscientists are skeptical, but some serious physicists and consciousness researchers have proposed that quantum effects in the brain, particularly quantum coherence and entanglement, might play a role in consciousness. The most famous proposal is the orchestrated objective reduction, OR, theory by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that quantum computations occur in microtubules protein structures inside neurons, and that consciousness arises from the collapse of quantum superpositions in these microtubules. Most neuroscientists think this is wrong because the brain is too warm and wet to maintain quantum coherence. Decoherence should happen almost instantly. But recent experiments have found quantum effects in biological systems that persist longer than expected photosynthesis in plants. For example, seems to use quantum coherence to transfer energy efficiently. And here's the kicker. If quantum effects do play a role in consciousness, then light would be central to how those effects are created and maintained, because photons are the primary means by which biological molecules interact and exchange quantum information. I'm not saying consciousness is definitely quantum mechanical. The jury is still out, but even the possibility is profound. It would mean that your subjective experience, your inner mental life, arises from the same quantum entanglement that we've been discussing this entire video. Your consciousness would literally be woven from light. Now, we're coming to the end of our journey, and I want to tie all of this together into a unified picture. Because everything we've discussed, from photons, experience in no time, to entanglement experiments, to cosmic entanglement from the Big Bang, to quantum technologies, to possibly consciousness itself, all points to a single, stunning conclusion about the role of light in reality. Let me summarize what we've discovered. Light exists in a unique regime where time and space collapse. From a photon's perspective, it connects two space-time events, creation and absorption, without experiencing any separation between them. This makes photons inherently non-local, perfectly suited to carry quantum entanglement. We've seen that virtually all entanglement in laboratories is created through photon interactions. Spontaneous parametric down conversion, the most common method, directly splits photons into entangled pairs. Entanglement swapping demonstrates that entanglement can be redistributed through photon measurements, suggesting that entanglement is a property of the electromagnetic field itself rather than individual particles. The universe began in a highly entangled state. Quantum fluctuations during cosmic inflation, mediated by the electromagnetic field, created primordial entanglement that persists today. The cosmic microwave background ancient light from the early universe carries signatures of this entanglement. Different regions of the universe that can't communicate with each other classically are, nevertheless, quantum mechanically correlated. Some of the deepest theories in modern physics, like the A=EPR conjecture, suggest that quantum entanglement is geometrically represented by wormhole-like connections in spacetime. If true, then the electromagnetic field, through which most entanglement is created, is literally stitching spacetime together. Light isn't just traveling through spacetime. Light is the mechanism that makes spacetime a connected whole. We explored how decoherence theory explains the quantum to classical transition through information spreading via entanglement. Light is the primary carrier of information in the universe. Most of the information reaching your consciousness arrives via photons. Your observations, mediated by light, create entanglement between you and everything you observe, integrating you into the universal quantum state. Quantum technologies, computing, communication, sensing are all built on harnessing entangled photons. These technologies will transform civilization in coming decades, providing unbreakable encryption, unprecedented computational power, and sensors that can detect the faintest signals in nature, all powered by light. And possibly, though controversially, consciousness itself might involve quantum effects, which would necessarily involve electromagnetic interactions, and thus photons. Even our subjective experiences might emerge from entangled light. So here's the unified picture. Light is not just a particle or a wave, not just electromagnetic radiation, not just the fastest thing in the universe. Light is the cosmic messenger, the universal connector, the fundamental mechanism by which quantum entanglement is created, distributed, and maintained throughout the universe. Entanglement isn't a mysterious correlation, and this leads to a philosophical conclusion that I find deeply moving. You are made of atoms, and those atoms are quantum objects, entangled with the rest of the universe through billions of years of photon interactions. Every atom in your body has a history of entanglement stretching back to the Big Bang. You are not separate from the cosmos. You are an integral part of it, connected through an unbroken chain of entangled light. When you look at the stars, you're not viewing distant objects separated from you by empty space. You're becoming entangled with them through the photons that bridge the gap. You and those stars are correlated, connected in the quantum state of the universe. Space and time separate you in the classical world, but in the deeper quantum reality, you're part of a unified whole. This isn't mysticism or metaphor. It's the direct implication of quantum mechanics and the role of light in creating entanglement. The universe is fundamentally holistic, interconnected, non-separable. And light is what makes it so. Einstein called entanglement spooky action at a distance because it seemed to violate locality, the idea that things only interact with nearby things. But maybe the problem was with our notion of distance. Maybe distance is an illusion that arises from our limited perspective moving through time. From the photon's perspective, there is no distance. Everything a photon connects is in the same place. Maybe reality, at its deepest level, is like the photon's perspective, timeless, spaceless, unified. And our experience of time and space is just the way this unified reality appears to observers embedded within it, moving through time, perceiving things from a limited perspective. If that's true, and quantum mechanics increasingly suggests it is, then light isn't just illuminating reality so we can see it. Light is teaching us what reality actually is, beneath our everyday perceptions. So the next time you turn on a light, or step outside into sunshine, or look up at the stars, Remember, you're not just seeing light. You're interacting with the fundamental infrastructure of reality itself, the cosmic network of entanglement that makes the universe a coherent whole rather than a collection of disconnected parts. Light could be the source of quantum entanglement, not in some vague or metaphorical sense, but quite literally. The electromagnetic field, with its unique relativistic quantum properties, might be the universal medium in which all entanglement exists and through which it propagates. Every photon is a thread in the cosmic web, connecting everything to everything else across space and time. You are woven into that web. You are part of the light. And that's not just beautiful, it's probably true. Now, before we finish, I want to issue you a challenge. Think about what we've discussed today. Think about how it changes your perspective on reality, on consciousness, on your place in the universe. Do you feel more connected to the cosmos? Does light seem different to you now? Does the ordinary experience of seeing something seem profound in a new way? Over the next few days, notice light. Notice how it illuminates the world, how it carries information, how it connects you to everything you observe. You're not just passively receiving light. You're actively participating in the quantum entanglement network of the universe through every photon interaction. And here's something you can actually do. If you have a laser pointer, be safe with it. Don't shine it in anyone's eyes. Shine it across a room. That beam of light is a stream of entangled photons. In some setups, even photons in a laser can have correlations. You're holding a device that manipulates quantum states, that creates and directs entangled light. That's not science fiction. That's reality, and it's in your hand. If you want to dive deeper, look up the double-slit experiment and watch videos of it actually being performed. See quantum superposition with your own eyes. Look up images from the Mises satellite showing entanglement distribution from space. Read about the 2022 Nobel Prize in Physics, which was awarded to Alling Aspect, John Clauser, and Anton Zeilinger for their work on quantum entanglement vindication, that this isn't fringe science, but established, Nobel-worthy physics. The rabbit hole goes deep, and I encourage you to explore it. Quantum mechanics is strange, yes, but it's also the most precisely tested theory in the history of science. And at the heart of quantum mechanics is entanglement. And at the heart of entanglement, I've argued today, is light. Let's also talk about what this means for the future. We're on the cusp of the quantum revolution. The classical information age computers, the internet, smartphones, transformed the world in the span of a few decades. The quantum information age will be even more transformative. Quantum computers won't replace classical computers for most tasks, but they'll solve certain problems: drug design, material science, optimization, cryptography exponentially faster. This will accelerate scientific discovery and technological innovation. Diseases that seem incurable today might be cured tomorrow when quantum computers can simulate molecular interactions with perfect accuracy. Quantum communication networks will ensure privacy and security in ways that are impossible today. Imagine a world where hacking is fundamentally impossible, where your data is protected by the laws of physics rather than just complex mathematics. That world is coming, built on entangled light. Quantum sensors will detect things we can't detect today. Gravitational waves from the early universe, dark matter particles, brain activity at the molecular level, environmental pollutants at ultra-low concentrations. We'll gain new windows into reality, seeing things that were previously invisible. And again, entangled photons will be the key. But beyond specific technologies, there's a deeper shift happening. For the first time in history, we're grappling with the fact that reality at its most fundamental level is non-classical, non-intuitive, deeply strange. The universe doesn't work the way our everyday experience suggests. Objects aren't separate. Causality isn't simple. Locality isn't absolute. This challenges our worldview in profound ways. It requires intellectual humility accepting that reality doesn't conform to our intuitions. It requires curiosity, being willing to explore ideas that seem absurd at first. And it requires wonder, appreciating that the universe is far more interesting, far more beautiful than we ever imagined. Light as the source of entanglement is part of this new understanding. It's not just a technical detail for physicists. It's a fundamental insight into how reality is structured. And you, by watching this video, by engaging with these ideas, are participating in this intellectual revolution. You're one of the relative few humans who understand, at least conceptually, what quantum entanglement is and why it matters. You know that light isn't just something that lets you see. It's something that connects everything in the universe. That knowledge changes you. You can't unknow it. And I hope it makes you see the world differently. If this video has blown your mind, if you're sitting there thinking, I need to watch this again, or I need to tell someone about this, then hit that like button, subscribe to the channel, and share this video with someone who you think would appreciate having their mind blown. Drop a comment with your biggest takeaway or your lingering questions. I read comments and I love seeing how these ideas resonate with people. And seriously, tell me what country and time zone you're watching from. I want to see the global reach of this quantum knowledge spreading through light itself. How appropriate is that? From India at midday to Brazil at midnight, we're all connected through this shared understanding, communicated by photons from your screen to your eyes, creating quantum entanglement between your mind and these ideas. Here's my final thought for you. You are a conscious observer in a quantum universe, integrated into the cosmic web of entanglement through countless photon interactions. You're not a passive viewer watching the universe unfold. You're an active participant whose observations shape quantum reality. Every time you look at something, you're creating entanglement. Every time light enters your eye, you're extending the network of correlations that connects you to everything else. You are, quite literally, woven into the fabric of reality through light. And that means you matter, not in some vague, feel-good way, but in a precise, physical sense. Your observations collapse quantum superpositions. Your interactions reshape entanglement patterns. You are a node in the universal wave function, and the universe is different because you exist and observe it. The light that touches your skin right now carries information from the sun, 8 light minutes away. But from the photon's perspective, the sun and your skin are at the same location. You and the sun are connected. You are part of the solar system, not just gravitationally, but quantum mechanically, through entangled light. Extend that thought. Photons from distant galaxies entered your eyes last time you looked up at the night sky. Those galaxies and you are entangled. The edge of the observable universe, 46 billion light-years away, is connected to you through the cosmic microwave background radiation that fills all space. You are not small. You are not insignificant. You are a conscious, observing part of the universe, connected to the whole through an intricate web of quantum entanglement carried by light. Light is the thread that weaves you into the cosmic tapestry, and every photon interaction is another stitch connecting you more deeply to everything that exists. So go forth with this knowledge. Look at the world with new eyes. See light not as a mundane phenomenon, but as the fundamental connector of reality. Appreciate that the ordinary experience of sight is actually an extraordinary quantum process involving entanglement between you and everything you observe. You are made of stardust. Yes, that's the poetic way of saying the atoms in your body were forged in stellar furnaces. But you're also connected by starlight, quantum mechanically entangled with those distant stars through the photons that bridge the gap. You are part of the universe, and the universe is part of you, woven together by light. Thank you for taking this journey with me into the depths of quantum reality and the profound role of light in creating entanglement. I hope you'll never look at light the same way again. Until next time, keep questioning, keep wondering, and keep looking at the world with curiosity and awe, because reality is far stranger and more beautiful than we ever imagined, and we're just beginning to understand it. The light is not just out there, it's connecting us all, across space and time, in a cosmic dance of quantum entanglement. And now you know.